Hello, my name is Evgeny Voivodin. I'm a PhD student at Bogdan Khmelnytsky National University of Cherkasy. My scientific research lies in the area of distributed systems, container orchestration systems in particular. In this presentation, I'd like to cover the software framework that I believe can be used to efficiently compare different resource balancing strategies in such systems. Let's dig in. Let's start from a definition of a container image and container. Container image is an application packed with all the dependencies that application needs. For example, imagine a Java application that when compiled becomes a set of binary files, bytecode. In order to run such applications, the one needs Java virtual machine, which will be responsible for executing that bytecode. In such case, the container image would include both Java application and Java virtual machine of desired version. It might also include additional libraries and tools that are necessary for that application to function. Container, on the other hand, is an instance of container image. It consists of number of running processes, basically application processes, plus it has additional resources and limits associated with it. For instance, max random access memory it can use, ports assigned to it, etc. Having applications packed into container images opens a way to accelerate development of software products, since one can easily pack and transfer the whole application between servers and run those applications without additional requirements, and hence time wasted on managing proper versions of required software or fighting library compatibility issues. In big organizations, such approach also allows to easily use different technologies for developing applications. Containers quickly became widely adopted in the information technology industry. The microservices architecture, which often utilizes containers, became a standard approach to develop large and complex applications in a reliable and scalable way. The need to manage the lifecycle of hundreds or even thousands of containers led to the development of dedicated software, which is basically what container orchestration systems, such as Kubernetes, are. One of the key components that container orchestration systems include is a scheduler. Scheduler makes a decision where the next container will be placed within the cluster of nodes, which are physical resources. This scheduling or balancing strategy is crucial as it might affect different properties of the application, for example, application fault tolerance or infrastructure cost. Recent works show the active development of new strategies, for example, utilizing machine learning techniques. However, there is no consistent approach and tooling to compare different strategies on a common basis. The key goal of this article is to provide a comprehensive design for an application capable of evaluating the performance of two or more scheduling strategies. In order to compare the strategies, there have to be metrics to use. The following metrics are suggested to be the basic ones that can be further extended if necessary: utilization of cluster resources or level of fragmentation, container deployment density, how many containers the strategy managed to pack basically, strategy request satisfaction ratio or acceptance rate, application fault tolerance, availability. Experiment is a key component that is configured to check the hypothesis among the given strategies. It consists of multiple parts, each of which must be separately configured and decided. Experiment is run in iterations. Before the first iteration starts, there is a setup phase, as illustrated in Figure B. The iteration setup includes the propagation of cluster topology to all the strategies. The topology essentially composes a set of nodes that have limits and can contain deployed containers. This topology is generated by the topology stream, a crucial first step. The topology stream allows for the definition of virtually any cluster structure, including the placement of nodes in physical racks for further fault tolerance testing. Additionally, the topology stream determines when the experiment stops, as it concludes when there are no more topologies to run the experiment for. The generated topology then serves as prototype for subsequent experiment iterations. The stream of configurations is responsible for generating container configuration or requirements to be placed within a cluster. Firstly, the stream can be either finite or infinite. An infinite stream will continue generating configurations as long as the packer demands it. Finite streams, on the other hand, can be used to test scheduling strategies for a very specific set of container configurations, to seek a better strategy, or for strategy monitoring purposes. Regardless of whether a finite or infinite stream is used, virtually any sequence of containers can be provided, including random sequences. A crucial aspect is ensuring that the same sequence is fed to different strategies, where each strategy operates its own copy of the cluster to fill. Secondly, the stream can be used to define application families. For instance, it can generate several configurations that depend on each other and form a larger application, as commonly seen in microservices architecture. The specific implementation of the stream determines how to establish these dependencies, and the container configuration structure allows for such connections to be specified. Thirdly, the stream can replicate a single container configuration multiple times. For example, if an application must be deployed multiple times within a cluster to ensure better response to failures. Each aspect can be implemented as a separate stream representation. The decorator pattern can be employed to combine these implementations in a desired manner, allowing for a variety of system demands to be covered. The packer is responsible for making decisions regarding when to stop in case of an infinite stream of configurations. Such decisions are highly specific to the use case being tested. For instance, the packer might stop after encountering the first scheduling request error or once the cluster is full. While it is the packer's responsibility to execute scheduling algorithms, the packer itself does not depend on the specifics of the strategy implementation. After the packing process is completed, the results aggregator collects the packing results based on the state of cluster field by different strategies. Firstly, the aggregator's job is to collect important data points, which it does after the execution of every iteration. Secondly, it produces an aggregate that represents these data points. For example, the aggregator might count the number of containers deployed by each strategy and then compute the average number of containers deployed. The aggregation phase occurs after the last iteration for the current topology has been executed. The flexible interface of the results aggregator allows for the production of a wide range of statistical information. For instance, with all the data points collected, an aggregate might include percentile or median values. The aggregated results are stored within the experiment and get associated with the corresponding topology. One of the desired characteristics of a strategy is its management of the fault tolerance of the deployed system. The malfunction component assists in testing this aspect. It's important to describe the malfunction in combination with the malfunction results collector. This collector is similar to the previously described collector, with the primary difference being that it collects results twice, before and after the malfunction is introduced. This approach enables the malfunction results collector to compare changes resulting from the operation of the malfunction algorithm. For instance, it can assess how many applications or application families survived a network partition. The malfunction operates within the cluster, deliberately causing a disruption, such as removing a node from the cluster or reducing the percentage of available connections. A client-server architecture is a recommended choice for such an application. Firstly, the implementation of the previously described components is separate from the visualization of the experiment results. The system's flexible state allows for the choice of whether to represent such results with user interface components or whether another system should simply delegate the execution of experiments to this one while making decisions based on the experiment results. Another advantage of adopting a client-server architecture is the ability to have multiple server instances, thereby enabling high-level parallelization of experiment execution. Additionally, having multiple server instances enhances the overall resilience of the system. Here you can see a few results of the experiments run using software based on the design in the article. The experiment compares bin pack and spread strategy. It uses random configuration stream and it stops when the first scheduling rejection occurs. So what you can see here is that average created containers is much higher for bin pack strategy over spread when such conditions are used. Here is another experiment that instead compares the fault tolerance of the strategy of the application using a particular strategy, and it also compares bin pack and spread strategies. And you can see that if after the packing the 20% of nodes are killed, while every container is represented by two instances, the spread strategy is much better tolerating application failure. So basically it means that in case of using spread strategy, at least one container survived such malfunction in 96% of times, while in case of bin packed, the value is much lower. The paper covers the design of the system that allows to compare different balancing strategies with flexibility being in its heart. The proposed division of responsibilities among different components such as topology stream, configuration stream, packer, strategy, cluster nodes, containers, aggregators, and malfunctions allows for extensive customization of the experiment flow to achieve the desired behavior. For example, such system can be used to compare the degree of resource fragmentation on the cluster nodes and thus assess the efficiency of resource utilization, measure the rates of containers creation or rejection, evaluate the availability of application encountering various network or node failures. Such um, system based on such design could significantly accelerate further research in the fields of resource distribution and distributed systems. The system would not only offer a platform for experimentation, but also become a valuable source of knowledge about scheduling algorithms